Yeah. Hello, my name is Florian Wende from ZIB. I'm really proud to give this talk here in Ken's session. And my topic is on enhancing explicit vectorization in Fortran if there is complex code patterns. And that's something about explicit vectorization, but it will come here after. So I do the first steps here. I think that most of you know that SIMD vectorization on the modern processors is really important because they increasingly draw on using the vector units to achieve huge values in the teraflops region for computation. And if you look at the right bottom graphics, which is Armdal's law for SIMD speed up over scalar execution, you see that with increasing vector lengths, the amount of your code that has to vectorize also increases tremendously. So, for instance, on KNL, if you perform computations with double precision, you have 8 words that can be processed at once. And according to this graphics, you need at least 80% of your code be vectorized in order to get about a factor 4 performance gain, which is half the gain you can theoretically get. So you see that it's really important to address SIMD in your code. And there are several ways to actually do that. Ken will go into details then. So for instance, we have AutoVectorization and Explicit Vectorization. Explicit Vectorization is available also in Fortran and C. So you can use it in both language. There's also manual vectorization, which is not directly accessible in Fortran. It's this SIMD intrinsic stuff you maybe know from C programming. The focus here in this talk, and this is, I guess, what Ken will also talk about, is explicit vectorization. And details here will be given on using OpenMP for that, because it's the new quasi-standard for explicit vectorization, and it's usable with different kinds of compilers without going back to vendor-specific directives. Well, with OpenMP4, you basically have 2 constructs you can use for vectorization. The first one is loop vectorization. It's just introducing the OMP SIMD clause in front of the loop, using some additional clauses to give further information to the compiler for optimization. And the second one is SIMD-enabled functions, which is a really recent feature. It is basically a mechanism where you as a programmer give a Scalar kernel to the compiler, and the compiler expands that kernel to finally have a vector version of it. And this kernel then can be used or can be called within loops that are candidates for vectorization. The syntax here for the directive approach is given in the second line. It's OMP declare SIMD plus additional clauses, and what you finally get is a vector version of this function. And I found in several samples, synthetic samples, real-world cases, that the compiler here can do really great work with OpenMP4. So if the loops are not that complex, so if there is no huge amount of irregularities in the loops, and if functions, for instance, are quite simple, as this one shown here, then the compiler can do a really great job here. The question is, what about code patterns that are more complex? For instance, I have 3 samples here. On the left-hand side, you see branching. It's a combination of simple branching, nested branching, conditional function calls. This really can be a challenge for the compiler, because the compiler has to introduce mask operations in SIMD execution, and that's non-trivial. A further sample is calling trees. If, for instance, you are within the calling hierarchy, and within the functions themselves there is almost no potential for vectorization, then it might be meaningful to vectorize along the calling tree. And this can be also really difficult for the compiler, also because of branching within the functions, conditional function calls, one function calls another function, loops within the functions that are not large but still there. So there are many situations which might hinder vectorization. And on the right-hand side, you also see a further sample, which is kind of future work, I would say. It's dynamic SIMD scheduling. If, for instance, you process a loop, and within the loop the work per loop iteration is different from one iteration to the other, then it would result into unbalanced load of the SIMD unit, so to say. This is shown to the left bottom within the right graphics. You can see that there is some white empty space. This means that these SIMD lanes run idle throughout the SIMD execution. And one idea here is to dynamically pre-schedule successive loop iterations onto lanes that run idle, and so to increase the overall throughput in SIMD execution mode. If you're interested in this, I will give a talk on Wednesday in the XPAC session for Xeon Phi, where I address this point and how to implement it in C, and in Fortran it's almost the same way. As I already said, the quality of the vector code that is produced for all these samples strongly depends on what are the capabilities of the compiler. I found that the latest Intel and also the latest Cray compiler can do really good job here. So results are quite good. But there are also cases where the compiler fails to vectorize. And this is what I would like to talk about, how to operate in this case to get vector performance anyway. So I would like to refer to the following as enhanced explicit vectorization. And the sample I would like to use is this one here. It's a simple function. It's just a part of the function. And within that function, you see there's branching. There's a conditional execution of the square root. There's a conditional function call to bar. And the question is how we have to translate that into something else that vectorizes, so into a function which can be used within a vectorizable loop. So it's not the entire function here. It's just a part. And my idea is to use vector data types explicitly in Fortran, and we first have to define them. This is shown here. We do that in a generic way to have it portable across different platforms. We introduce this parameter VL, which is vector length, and it is set to 8 here. It's, for instance, the native SIMD with on a KNL or KNC, or if it is computation in single precision, then it would also work on Haswell. And then we define a SIMD module, and within that module we have different data types that can be used for vector operations. Here are just 2 of them. It's a double precision data type, SIMD real 8. It's a simple array of 8 contiguous double precision words, and we have an appropriate mask to perform masked operations on this data type. The second point is to somehow translate the scalar version of the function I showed previously to a vector equivalent. This is shown here to the right-hand side. The gray code is the scalar case, and I go stepwise through it to show what is different in the vector case. And the first thing you see is that the data types that are input and output to the function now are not scalars anymore, they are vectors. This is shown here. And of course, we have to use the SIMD module, so there is a use SIMD, and we have additional masked data types. The idea here is that within the function, we would like to know about which SIMD lanes are active and which are not. If, for instance, there's branching in the function, then only SIMD lanes that are active should participate in the evaluation of predicates. This is just to don't process code sections that are not executed by any of the SIMD lanes. The next step is the branch, and you see on the right-hand side the scalar code. It's the predicate x larger than 0 that is evaluated, and depending on what is the result, we execute the square root. And on the left-hand side, so in this foo SIMD function, we have to introduce a loop to operate these vector data types. So this is the innermost loop, which now is the candidate for vectorization, and we use OpenMP to operate vectors. And you see that basically it's a straightforward translation from the scalar case to the vector case. The scalar code is executed element-wise for each vector. And in the scalar code, after the square root computation, there is this conditional call to the function bar. And to address this in the SIMD case, we introduce a mask M1, which we set or initialize to false for all SIMD lanes. So all SIMD lanes basically do not participate in the execution. And we now evaluate the predicate only on those lanes that are active, that is the predicate M0 and then the scalar predicate. And we activate the SIMD lanes for which this predicate is true. After we have ended the loop, we have a kind of routine test any, it is called here, which checks for the mask M1 if there is any SIMD lane that is active. And only if this is the case, we make a call to the function bar SIMD, which now is also a vector function. And we can give to this function vector arguments and the new mask M1. So that's the basic idea behind that. It's a straightforward translation, I would say, and you can adapt it to several other cases and also more complex cases. I benchmarked this kernel, the entire kernel, so this was just a part of the kernel, on an AVX system. The clock rate here was set to 1.9 gigahertz, which is AVX base frequency, just to avoid the case that there's some overclocking in the Scalar execution case and we compare apples against oranges. So the Scalar clock was also 1.9 gigahertz. And the Scalar reference values are shown on top of the table. With two different compilers. It's the latest Cray compiler we have on our machine and the Intel 16th compiler. They both give comparable Scalar performance, about 2.6, 2.5 seconds for a loop where there are about 8 million loop iterations executing this kernel. And the performance can be seen in this table for explicit vectorization and for the enhanced explicit vectorization with the additional vector data types. So for explicit vectorization, we see that there is a performance gain over Scalar execution, but we can increase it with the enhanced explicit vectorization scheme by about 10 to 20%. So it's not that big number. I have other samples where the increase is much larger compared to explicit vectorization. I guess the reason here is that there's a lot of control logic overhead here, which is introduced due to my scheme, and this somehow overcompensates the performance gain due to the approach. For the Cray compiler, we can see that with explicit vectorization, the performance remains almost the same as Scalar performance. The reason here is that the Cray compiler currently has no support for SIMD-enabled functions, so it just doesn't create a SIMD-enabled function. So it calls a Scalar function, performance the same. But with the enhanced scheme, we can increase the performance and have almost about the same performance as we have with the Intel compiler. So this supports the point that you can use different compilers and you do not really depend on special capabilities of the compiler. Another sample is the VASP code we work on within our IPCC. And here are just the performance gains we achieve with that scheme over explicit vectorization. On the Haswell system, it's 1.2. On the Xeon Phi KNC, it is almost a factor 3 performance gain. I have to note here that on the Haswell system, the code with explicit vectorization is faster than Scalar execution. On the KNC, the explicit code is a bit slower, so we actually need that scheme to get vector performance on the KNC. Well, a question maybe you may ask now is why should I use this kind of programming? I demonstrated here that we can get portable performance across compilers. So this is one reason I would say which might be a benefit for this kind of programming. The other a further argument is that we fully draw on standard loops. So you saw that we moved the loop for vectorization within the function bodies, and these are really simple loops, so to say. And many compilers should be able to vectorize these kinds of loop instead of vectorizing the entire calling tree without this approach. A further point I deem really useful is that you can use vector and scalar code. This is, as far as I know, not possible with explicit vectorization. So if you are in a SIMD-enabled function, then everything is vectorized. And in this scheme, you have the loop within the function. And if you now want to execute a section of the code in Scalar case, you just break the loop, isolate the section, execute it in Scalar mode, and then continue the rest of the execution in SIMD mode. This might be really useful, for instance, if you have scatter or gather operations where the compiler is somehow not able to generate effective vector code for some reason. I had this case in the VASP application. And a further point is debugging the code. So if you use just explicit vectorization, then everything happens behind the curtain. So you will never see vector code. And now if, for instance, your code runs without segmentation faults, but the result is not correct, the question is where does the result become wrong? And with that approach, you can isolate the point because you have the loops. And you can split them further and further until you find the error of the faulty results. Well, and basically that's what I wanted to say. If you have interest in more information about this kind of programming in Fortran, you can also use it in C. I had a webinar about 2 weeks ago, and the material I used there is hosted on GitHub, so you can just look it up there and play around with the samples and get further information in a more detailed presentation that is available on GitHub. Yeah, that's it. So, yeah, if there are any questions, I'm open to answer them. Yep.
So can I ask, you used OpenMP SIMD. Have you tried with Intel?
Yep.
VIR SIMD, is there a performance difference between the two?
With Intel, you have these OMP, you have the SIMD directive and you have the vector directive, right? I tried different combinations, and in some cases it was better to use vector instead of SIMD, and in other cases it was not. But I didn't find really huge deviations between the two approaches. So OpenMP4 and Intel.
So OpenMP4 will give you the same performance?
OpenMP4 is, as far as I know, almost equivalent to the SIMD clause, the SIMD directive from Intel. For vector, I don't know. I guess in real scientific codes, you always have exponentials, logarithms, and so on. I think you have to go to SIMD because with vector, these loops do not vectorize.
So I'm a little confused on your example.
Yep.
And it's possible it's just because you didn't go in depth enough. But you've got a block that you're doing in vectorization, and you have one element that hits that if switch.
Yep.
You said that you're keeping those up to do a vector block of those. But I didn't see how you're dealing with padding or gaps. If you don't have enough
yep.
to fill a vector, you're going to end up with a lot of bad performance.
Okay. Yep. So I just illustrated the approach here for that function. The question is what goes into that function, and what goes into the functions are the vectors, which are packed vectors. So basically, you have a loop around that. And there is kind of prologue and epilogue in the loop. So in the prologue, you pack the vectors. This might be the case that then you have gather operations. And then these packed vectors are input to that function. So here you operate on SIMD registers, so to say, if your vector length maps to the native execution, SIMD execution with. And after you've executed, the result is unpacked. So it's just outsourced to the beginning and the end of the loop. And within the loop, then we operate on vectors, and these are packed vectors.
So what happens with the block that's still executing when that one section hits the if? Does that whole block freeze until it's resolved? So if you're doing multiple operations in your first vector block loop.
Yeah, the block is executed on all SIMD lanes, and what happens afterwards is because you have this mask, you just blend in the results for active SIMD lanes. So that's the way how the compiler actually does this. Okay. So if you look in the assembly, you see exactly this. So the compiler creates a mask, it operates on all SIMD lanes, and after the computation, it just blends the results, the original results that should remain throughout the execution on lanes that are not active with those that are active, and it merges the new results into the initial values. Into the initial vector.
So, sorry, I've just got one other question on this. But so, what if that breakout section? Let's say you found your convergence point, and that particular value is no longer needed. Will that masking still allow the rest of them to continue in vector?
No.
Okay.
No. You simply have this if you, as you see it here in this code. I guess it's here. And if, for instance, here there are further instructions to execute here after this end if, then you execute without using the masks. Okay. Yeah.
Thank you.
Okay. So basically, this approach maps onto what is done by the compiler. So I started doing this with C intrinsics, and when I was to optimize Fortran code, then there were no SIMD intrinsics. I had to introduce kind of mechanism that allows to code in a similar way, and this is what I presented here. Okay. If there are no further questions, I would give back to Ken.
Okay, we're going to go back to going over the optimization reports. And so the optimization reports are very important when you're developing your code, so you can see what is being vectorized by the compiler automatically. You can look at the effective speedups that you might get in a potential perfect environment. And the more important thing is you can see what isn't vectorized that you were expecting and why. All right, and so starting with the version 15.0 and onwards, we recently released 16.0 update 1, and that happened last week. The option that you guys may have been used to was the -vec report. We've changed that to -q op report, which you see down at the middle of the screen. And now, instead of having to run multiple reports to get all your information, we've concatenated it all into one option. And if there's a certain phase that you were looking for, you can use the -q op report phase to just single out that phase. So if you're only looking for vectorization, you can put -q op report phase equal vec. And that way you can filter out all the other things that you may have going in your code, whether it's offloading or some HLO optimizations or inlining. And also, you're able to change your output to go to a file now instead of it going to standard out and you having to redirect that file, the output into a file. We now have op reports being generated for each individual source file that you compile with. And if you wanted to go back to the old way in 14.0 and below, you can use the -q op report file equals standard out. One caveat that I'll give you, I know the Linux community uses a lot of makefiles with everything that they use. If you use a makefile and you use the -q op report file equals a file name, you will constantly overwrite that file. That is a feature request that we've received recently, and we're working on implementing that now. Okay, and so this is, we're going to look at the loop optimization report. This is a simple program that we have. Let me just go to the end. And so here you can see in the optimization report, it tells you the loop nesting, it tells you why the loops were not vectorized. It gives you the line numbers. Let me see what's in here. If there's any sort of loop interchange that you see in the first clause, it will tell you how the interchange happened. It gives you the source location of the file. It gives you the file name, the line, the column number, and you have all your header information. And you have a bunch of information that you didn't get in 14.0 and below, just to help you get the best that you can get out of the compiler. And so here's an example of what you'll get in the new optimization report. Here you see we turned on -x AVX, which we'll talk about later. You need to specify the architecture type that you want to compile for to get the best optimization. And so here you see it has the loop beginning, func1.f90, and it'll tell you that you have the multi-versioned loops, so you know that instead of having to go and dig through the assembly code, which a lot of people were doing in 14 and 13, we're giving you all the information that we can. And one of the things that you'll be able to take a look at is you see that you have unmask, unaligned stores and reads. These are different places where you can look at your code and figure out is it possible to get this memory aligned? That way you can get even more performance because, as you all know, the aligned stores are much faster than unaligned. And so here we have a couple of other tricks that you can use. The biggest takeaway here is to make sure that your code is standard as across the board. You don't want to have the compiler doing unnecessary type conversions because that's going to cause you to get a lot of performance left on the table. Oh, and another thing here is we have this potential speedup at the bottom. So the potential speedup is an aggregate that the compiler uses to figure out if it's more effective to vectorize a certain portion of your code or if the Scalar version would end up being faster. So you don't want to take the estimated potential speedup too seriously, but it is a good way to gauge how well you're doing on vectorizing your code. And again, you can't take it too seriously because the compiler can't take a look at your system and see how everything else is running at the same time as when you plan on running the code to get an actual solid estimate of what you'd have. And so in this slide, the compiler doesn't know about the alignment, and that's why you have the unaligned stores here. That's one of the first things that we go over when we do labs with customers is we'll go through the optimization report, and if we see a bunch of unaligned stores in the optimization report, we go and we look at that specific function to see if we can improve that. Adding the alignment normally gives you quite a bit of speed up on a particular heavy use case, especially if this is one of the hotspots in your code. All right, and so let me go back. And so here you see the estimated potential speed up being only 4.560. When we look at the aligned version of the same code, you see that the potential speed up is now 6.970. So you get almost a 2 times performance theoretical increase simply by making sure that the compiler knows that your code is aligned, that your data is aligned. And we're actually going to talk about that a little bit later when we talk about the explicit vector programming, how you can achieve that, the different things you want to look for. And so one of the newer features that we added was the annotated assembly listings. I know a lot of customers are constantly looking through their assembly to see what was vectorized and how the instructions changed. And so what we decided to do was, instead of just giving you your normal assembly file, we've added comments in there so you can see what actually happened. So instead of having to search through your code and do a diff to see what's different between them, we kind of give you the start as a where to look so you can see the different things that have happened in the code. Let me just go to the end of this slide. And so you can see where all the loops were vectorized. You can see where the interchanges happened. You can see where the remainder loops are, so you can see how that panned out. And so we have multiple levels. The important thing here, if you're doing a large project, do not start with level 5. There is an immense amount of information that you will receive if you go straight to level 5. Our default is level 2, and that gives you reports of when vectorization happened. It gives you the reasons why vectorization didn't occur. And so what I tell customers to do is just run it with the op report normally, which will give you level 2. Any place where you don't get vectorization and you're not sure why, by reading the level 2, take that specific file and bump that up. Otherwise, you're going to have a plethora of information, and it's going to be too much for one person to go through. All right, and that's all that we're going to go over for the optimization reports. Were there any questions about the new optimization reports?
During yesterday's sessions for the Vectorization Advisor, so the information that the Vectorization Advisor is showing basically this in terms of an employee environment for Vectorization?
The Vector Advisor uses part of what the compiler has, and it has its own algorithms as well that it uses. So it's not completely the same, but the information does overlap quite a bit. Were there any other questions?
What happens if you tell the compiler that your data is aligned, but actually it's not?
We actually talk about that a little later, but what will happen is you'll get a segmentation fault when you run your code. There are some cases where the compiler will be able to look at your code and say that this isn't aligned, and it'll argue back with you. But if you override that using the pragmas and the flags that we'll go over later, you will run into a segmentation fault when you get there. Any other questions about the optimization reports? All right, so moving forward, we have the compiler AutoVectorization support. I guess the meat and potatoes of the talk. So everyone here knows what SIMD is, single instruction, multiple data. The common vector lengths that we run into are 2, 4, and 8 for your Xeon. Going forward to Xeon Phi, you normally use either 4, 8, or 16. And that specifies how large your vector length is. This is something that you also have control with pragmas. For instance, if you want a certain function to only run with a vector length of 4, because you've noticed that you get better performance that way, then that's something that you can control for that specific function and allow other functions to run at the largest vector length possible. And here we have the size of the vector lane. So like I said, 256 is the largest that we have for AVX2. But when we move into KNC and KNL, we have 512. And eventually in the Xeon Skylake, we'll also have the 512 bit. Okay, and so previously with SSE, we had the vector size of 128 bit. Moving to AVX and AVX2, we doubled that size. And with Skylake, we're planning on doubling that size again. Currently in Xeon Phi, our coprocessors, we have the 512 bit already, so you're able to use the Xeon Phi to get a idea of what you'll be doing in the 512 range, because that's going to change what you do later on with your code. The good thing about the compiler is we have support for all of this already inside the compiler, so you don't have to wait for the next iteration of the compiler when you get your new hardware. You're able to take advantage of the hardware as soon as you get it. And so some of the terminology that we use are the vector lanes, and as you can see with the little red circle, that's what we're talking about. That's one lane. In this particular case, we have 16 lanes that you can compute across. Again, that's common knowledge that you guys all have. One of the more important things that you guys will have to take advantage of is the compiler switches. I'm going to start at the bottom and work up. I think that's the best way of talking about this. And that's where we have our special flag, -X host. And that'll do a processor check at compilation to see what the best architecture you have available is, and it'll compile for that architecture. The problem with doing that is, let's say you're building on a AVX2 machine, but then you decide that you're going to go ahead and run that on an AVX machine. And you've just been using the -X host because it gives you the best performance. The problem with doing that is as soon as you go down to that AVX machine, your code will not run. The nice thing is it won't segmentation fault. It'll do a processor check before you actually run it and say that this binary is incompatible with this hardware. And so if you ever get that message, that's generally what it means. And so moving backwards, we have the AVX 512 with mic that you can use now with -X mic -AVX 512. Previously, before 16.0, you had to use the -M mic flag, which would not give you the processor check beforehand. But obviously, trying to run a Xeon Phi binary on a Xeon architecture, you're going to get an error anyway. The newest flag for AVX2 is -X core AVX2. It isn't -X AVX2. So you can't just go and add the two-year-old make files. We also have -X AVX. The important thing to note is the default is -M SSE2, which will leave a lot of performance on the table. So if you are working on updating your code, you're going to want to make sure that that's one of the first flags that you set is to change that. Otherwise, you're using optimizations from years ago, and you're really leaving a lot of vectorization on the table. Oh, before we move forward, were there any questions about this slide? Okay. The more interesting slide, I already talked about -X hosts, and we've talked about the default. So we're going to talk about the multiple code paths. What this allows you to do is you can specify a base. So let's say you want to make a binary that's compatible with AVX and AVX2. What you'll do is you'll set the base as AVX, so you use -X AVX. And then using the alternate code path, the -AX, you can specify -AX X, let's see, X core AVX2, and that'll allow you to get the code paths for AVX2. So if you do have a AVX2 machine that you're testing on and you want to also test it on the AVX machine, you're able to do that instead of having to generate two different binaries. The important thing to know is that this will cause code bloat. So you're going to end up with a much larger binary than what you had. And some guidelines for vectorizing code is, the compiler prefers simple do loops. That was one of the great things about Florian's talk, because he talked about what do you do when you have more complex loops that the compiler can't automatically vectorize. He gave you an example of how to get around that little block. And here are some of the things that you want to try to avoid, all of which Florian kind of went over, which is great. And again, the other big takeaway, which is near the bottom, and probably one of the bigger takeaways as we saw looking at the optimization report, is you want to make sure that your code is aligned, that your data is aligned. If you can take care of that, you'll get an immense speed up, because that's something that the compiler does not normally know off the bat. And so how to align data in Fortran. It's kind of a two-step process. You can add the directive attribute align, and you can let the compiler know how the size of the alignment. You can also specify at the compile line the -align array 64-byte or 32-byte, however you want your data aligned, and the compiler will attempt to align the data types. Again, this is one of those times where you're going to want to check the vectorization report to actually see what happened and make sure you're getting what you expect. Because again, it's an attempt, it's not guaranteed. And then you also need to tell the compiler, even using the -align array 64-byte, you will still need to tell the compiler in your source code that the vectors are aligned using the either assumed align directive or the vector align. And again, every time you make a change to your code like that, you're going to want to recompile and check the optimization report. If for some reason you are not getting the alignment that you expect and that's showing up, that's something that we would ask you to report. Because there are edge cases where this doesn't pan out, and there's two places where you can report it, either through Intel Premier support or through our user forums. If any of you guys have been on the user forums, you know that Dr. Fortran is on the Windows and Linux side of the Fortran forums like a hawk. I'm not sure how happy the compiler development team is with his efforts, because he gives them a run for their money every day of the week. And so here are some of the useful compiler directives. So IVDEP is probably the most powerful one that I would like people to use. And it tells the compiler to ignore vector dependencies. It's a little bit different from the SIMD directive, which says vectorize this at all costs. I don't really care much of what you think about the safety of it. I know that it's safe, so go ahead and do that. The problem with that is you can run into a situation where your code isn't safe to vectorize, and now you're going to end up with a segmentation fault, or you end up with even worse, a result that you weren't expecting. And so IVDEP, what it does is it'll say ignore the vector speedup costs. But if the compiler can prove that it's not safe to vectorize this, then don't vectorize it. There's also the vector always, which is quite similar to the IVDEP, but not as powerful. When you look at the optimization report, you'll run into issues where it says the compiler didn't vectorize this, mostly because it doesn't know if it's feasible. And one of the things you can do is you can change like the loop count to let the compiler know that this is going to run at least 1,000 loops or something along those lines. And so now the compiler has more information. It says, okay, based upon that, we'll go ahead and vectorize this. Were there any questions about this slide before we head to the explicit vector programming? All right, great. Oh, sorry.
The loop count, I presume it doesn't make much difference after a certain point. You're really looking for small loops, right?
Right. But there are some times when the loop count is hidden from the compiler, and those are the cases where you'd actually use the pragma, just so you can get the vectorization. All right, and so we're going to go through the explicit vector programming. How much time do I have? 5 minutes? All right. So we have the OpenMP SIMD loops. There was a question earlier about do you get better performance using the Intel pragmas or the OpenMP pragmas? What we have done mostly is we've taken our pragmas and we've adjusted them to fit the OpenMP pragma. So like Florian mentioned, you shouldn't see too much of a difference. If you're seeing a massive difference, then it's probably error in the compiler that we didn't know about that you've exposed. And so going back to OpenMP SIMD, which is what we suggest that everyone use now that it's been standardized rather than using the specific Intel pragmas. You're going to want to use the modern F90 if you can. The do and the end do's, do not use the do while loops. We're still working on those. This is something that we're constantly working on, constantly getting better each iteration of the compiler. But with all the standards changing and 2015 standards coming up, our compiler developers are pretty swamped trying to stay on top of everything to give you guys the best compiler that we can. And so one of the important things is you're going to want to use the -q OpenMP if you actually need OpenMP, but if you're only using the SIMD directives of OpenMP and you don't actually need that parallel aspect, you can use the -q OpenMP-SIMD. Also, if you want to just test the SIMD portion and you actually do have the OpenMP, you can use the OpenMP SIMD to kind of turn off the parallelization factor and just check the vectorization that you'd get with the SIMD. And so these are the clauses that we have for the OpenMP SIMD directives. The good thing is if you're used to using OpenMP, these are the same directives that you're used to using. They work the exact same way that you'd expect them to work. You can also use the safe length to let the compiler know that this OpenMP loop is okay to vectorize up into a certain length, 4, 8, or 2. You're also able to use the align to let the compiler know that it's aligned as well.
Is there a reason why reduction wasn't in that thing that said like OpenMP?
That actually may be a typo because it is like OpenMP. It's the exact same that you'd expect it. I think I have to check, but I'm pretty sure there's a couple of extra reductions that are available by default without having to go to the user-defined reductions that OpenMP doesn't have. But I'd have to check to make sure on that. And we already talked about why vectorization is so important. The processors aren't getting faster and faster and faster the same way anymore, but we're getting more and more efficiency out of compilers by widening the lanes. And so taking advantage of this is probably one of the most important things that you could be doing right now to keep your code aggressive and competing with your competitors. And so the other good thing about OpenMP SIMD is it allows you to get vectorization where you normally wouldn't get with the compiler. There are a lot of times the compiler will only vectorize the innermost loop, and you'll actually see that pop up in the vectorization report quite a bit about the reason why a certain loop wasn't vectorized. But using OpenMP in tandem with vectorization gives you the ability to vectorize outer loops a little bit easier.
So in that example, you haven't made J private. Is that a loop count is always private in OpenMP SIMD?
It isn't private by default. I will have to talk to Martin about that. So I'll get that cleaned up in the slides. Okay, and so looking at the vectorization report, you can see that we've already brought in all the information about the OpenMP loops that were vectorized and all of that. So you don't have to look at a separate report or worry if you're not going to get that information. All right, and so going quickly through the new features that we have. In 16.0, we introduced submodules. That was probably our biggest new feature that we have with 2008. We also improved our uninitialized variable detection using the -init as well as the -save. We also have the Scalar math library is now optimized for Intel AVX2, taking advantage of the fuse, multiply, and add instructions and other instructions that are available there that aren't available in AVX or below. And we have a couple of other new features in 16.0 as far as impure elemental. We have more C interoperability with Fortran 2015 that's already been implemented in the 16.0 compiler. And were there any other questions before I wrap up the summary?
On that last slide, what was the exit from a block construct? What is that feature? Can you give a little bit more?
So previously you weren't able to put an actual exit clause in a block statement. Our compiler would complain and break, saying that it wasn't able to compile that. We've changed that. I'm trying to think of the reason behind it. I'd have to get back to you the main reason why we added that. It's not common to see an exit from a block construct, but I believe it was a feature request. I don't know who requested it off the top of my head since I didn't file the feature request. And so the summary is, make sure that you're using the 16.0 compiler. The reason behind it is we've added a lot of vectorization support that's not in the 15.0. We're also moving forward. We have the KNLs. Sorry about that. We have the KNL support that's in portions of 15.0. We also have that in 16.0. So if you're in 16.0, you're future ready, which is great. We have a lot of OpenMP 4.0 features as well inside of the 16.0 compiler. And here are some of the different references that we have, resources that we have for explicit vector programming. Our user reference guide, which is useful if you run into any error or any remark that you don't recognize. You're able to search using the user reference guide and get a detailed explanation of what it does as far as any compiler switches as well, and the default behavior. We also have our user forums, which are very active. I'm not sure if any of you guys are using them. If not, please definitely go take a look there. There's a lot of interesting information being talked about every day. Were there any questions? No, I've gone slightly over time. Thank you guys for being patient. Thank you, Florian. And hopefully you guys enjoy the rest of the conference.